cover primary and secondary recovery. But before that, I'm going to introduce myself. My name is Saiful. I'm a reservoir engineer. This topics I'm going to cover today is two parts. The first one is primary and secondary recovery. Before we go further, so probably you can have a short ice-breaking session. Yeah, we'll start with the common first.
Okay, Assalamualaikum and a very good morning everyone. My name is Farhan from Reservoir Geology.
Assalamualaikum, good morning. My name is Amy, Reservoir Physicist.
Hi, morning. My name is Faz, Reservoir Geoscientist. Shakira, Reservoir Geoscientist.
Isto Hassan, Operations Analyst.
Safwan, Reservoir Geologist.
Okay, thank you. Nice to meet you all. Okay, let's continue with the session. Okay, so we're gonna start with primary recovery. Okay, look at this. This name already is calling primary, right? Primary is like the first line, right? When we talk about reservoir, reservoir side. Okay. So for the linear outcome, so there will be three main linear outcome. So at the end of the day, you will be able to identify characteristic of different drive mechanism. One will be able to distinguish reservoir performance of different drive mechanism. The third one, I think this most of us interested to know the estimation of recovery factor for each different drive mechanism. Okay, so we will cover these three main items. Okay. Okay, just a bit introduction. Okay, so as you guys define your reservoir, right? It's not unique, right? It's different. They have different real properties, right? Rock properties, the fluid, and also drive mechanism. This is very important for us. Sorry, it's not just about the rock properties, right? You want to produce, but with the with the same rock properties or even different rock properties, do we expect the withdrawal or recovery from that reservoir to be the same? No. It could be same or no, but there is a few elements that we need to consider, to define what to be the primary drive mechanism. Okay. No two reservoirs are same, but they can be grouped according to primary drive mechanism. Okay. You will see later on the range of recovery factor that we can relate to each drive mechanism. The third one, each drive mechanism have typical performance characteristics in terms of ultimate recovery factor, pressure decline rate. Remember the key, pressure decline rate, gas ratio, and water production. You can see for the performance plot, when I say performance plot, pressure profile, or the water production profile, gas production profile, or pressure profile, you can recognize what their drive mechanism based on that plot. You'll see that I will cover this one. Okay. Okay, drive mechanism. What is drive mechanism? Okay. So it's a natural sources of reservoir energy causing oil and gas to flow into water. Okay, you see here? This water, right? This is aquifer. This is the one normally that in the model that you define, right? Maybe some is limited to aquifer. Maybe you don't penetrate water at all. But how do we know, right? That there is water impacting our reservoir. Right? Okay, this that we see that what the natural source of energy that cause the production oil or gas that flow into the wellbore. Okay, yes, you can produce, but what will be the ultimate? So it's depending on your drive mechanism. Okay, drive mechanism. Okay, there are various drive mechanisms that come from the impact of number of phenomena. Okay, for example, the first one, expansion of reservoir fluids, oil and gas water. Okay, in the fluid itself, you have compressibility, right? Because in reservoir, remember, you always have in the equation of what? Start with G, right? There's a BG and BO element, right? is an expansion factor, right? So the fluid itself will expand as you produce from the reservoir. So that's so can give the energy to the reservoir. Liberation, expansion of solution gas. Okay. Normally when you calculate the reservoir volumetric, right? Okay. You don't account for the solution gas, but there is solution gas actually in the oil, right? Okay. Unless you have a gas cap, you will calculate gas cap now. But for solution, normally we SRE will calculate solution gas. Okay. But in the oil, there's a gas. It's will liberate, so it will become also the form of energy to drive the fluid to the reservoir and to the well. Expansion of reservoir rock and reduction of volume. Okay, I think this more related to mechanical part. As you produce, right? So your volume also will reduce, right? It's become also part of the form of the energy to the reservoir. And gravity forces. I'll show you further what's the mean by the gravity forces. Okay. Now, type of natural drive mechanism we have. This is the main, I would say that. Okay, you have depletion drive. When you got depletion drive, is solution gas drive or gas gap drive. Water drive, then water that drive the oil into the reservoir. Compaction drive, because it's like more the perspective effect, right? Gravity drainage and combination drive. Okay, maybe in the field that you experience that. What is, you've seen, normally the discussion goes around, right? I mean, what's mainly the drive you see in your field? Anyone? The drive. That's in the which region? Is it BM, or the drive? For the gas and oil also. For oil and gas reservoir. Or mainly on the oil. Oil. Okay. Escape, right? But normally it will come with the combination traffic. Both. Normally. Okay, normally if you have water drive, as you dig your reservoir, right? So you expect gas will come out from the oil, right? So that gas also will form the energy. So normally you have combination drive. Okay. Okay. So it's very important so that you know that how to optimize the reservoir, because for each different drive mechanism you will have a different optimization. So it's very important that to know that so that you can really optimize your RF in this case. Okay, see here. That's an example of solution based drive. This is the original condition. All the gas inside the oil. So you don't calculate this one. You don't know how much. Normally GNG don't calculate what the solution. So we give RSI, which is initial GOR to calculate your solution gas. Okay. As you produce, then as the pressure goes down, you expect that the bubble will come out. Okay, when the bubble will come out?
Pressure reduce.
As you reduce the heat, the bubble point, and then it start the gas to come out from the solution, right? Okay, so it will liberate it, from the oil, and then it will help to produce the oil. Okay. See, liquid solution gas.
So this is in the event that your water drive is weak, right? Then you would have the solutions gas, right?
It will become dominant drive. Okay. So in each drive mechanism, like I said earlier, I said combination, right? So it will have the dominant drive. Okay. In the case of weak aquifer,
Right.
this will be the dominant. But the strong drive mechanism, this will be the
Secondary.
secondary.
Okay. But that's like what normally Maram would be having.
Yes.
How do we know which one is dominant?
Okay. there is a, we call it yesterday, this one, sorry, there's a method balance that there's, we call it drive indices. Okay, it's a by time that you can see, because it's not constant throughout the time, because we are dealing with time, right? Okay, for at certain time, you will see what will be the dominant, we call the drive indices. Okay, this plot that by the time, you can see that what will be the dominant drive at certain particular time.
It's based on pressure, oil
Yes.
rate, all
Yes.
that.
It's basically it's called postulated method balance equation.
Okay.
Yeah, method equation. Okay, solution gas drive. Okay, you see here. Maybe we go straight into this plot. This is the plot of producing GOR versus pressure. Okay, at the beginning, this RSI. It's a constant. So you expect RSI will be constant below or above? Which one? Below or above RSI? RSI will be constant at the below or above PB? Above PB, right? So it will be constant first. Depending how much RSI which you determine from the left. Okay. From 1 here is starting, and then as you goes here, and then it will be constant. Once it hit the below PB, then you expect that the gas will be liberated. Yes. The first gas will come out from the solution, right? From 2 to 3. Okay, forget about 3 first. And then as you further deplete the pressure, right, you expect that your gas, come out more from your reservoir, right? And then until the duration the peak here, and then again it comes back to the decline. What happened actually? Let's talk about the 4 to 5. What do you think?
The oil is settling at the lower part of the reservoir.
Right? Almost there. Almost there.
Gas finish.
Yes. Gas finish already. Not really totally finished lah. It's still there. But you're right. Because most of the gas already come out from the reservoir, from the solution. That's why it's deep. Okay. So this kind of typical plot of the GOR versus pressure for the solution gas drive. Okay. Now come back to here. 2 to 3. What happened actually? What do you guys think? Why is something like goes down?
Pressure drop.
Pressure drop a bit, but pressure
Sorry, the geo. I was going to ask you that because at the onset when you reach bubble point, why did the GOR drop?
yes. What? What do you think?
It's our solution.
Sorry?
That's our solution.
Yes. Yeah. It's a solution gas. Yeah. But what happened here is it's a slump here a bit. We are talking about the critical gas situation. Okay. Now what happened here? Gas already there. Gas come out already from the solution. But just imagine it just only it's not a lot. It doesn't reach the critical gas situation. For the gas to move. Gas is there, it's liberated but not moving yet. So that's why it's slumping. Once it's reached the critical gas pressure, then it starts to move. Just gas at the reservoir condition. Okay, I mean.
Is it possible that if you have like a strong water drive before, then you never actually produce that solution?
Okay, you will see that the gas drive. I said, but the key that is depend on the dominant drive. You will see the plot for the case of water drive.
Okay, that's why we remain constant for a long time.
Okay, you can expect like that. Yeah. But it's maybe a bit different because you have other element, right? Water drive. Yeah. But like you say lah, logically that you expect that RSI could be prolonged lah, because high pressure, right? Because of drive, water drive. Okay, yeah. Okay. For this typical recovery, you expect very low. Okay, 5 to 30%. 30% probably you have a good well placement. You can have up to 30%. Normally, for the worst well placement, limited area coverage, so you might have 5%. Okay.
So in this case, you want to ensure we don't reach our point to maintain or probably get higher recovery.
How to do that? This is natural, right? As you produce, pressure deplete, right? You, even you will try to avoid, you will keep below PP, right? Yeah. But yes, that's the idea. That's the reason why we go for the
Injection.
secondary. Okay, we will cover it now. Okay. At least you have that. That's how we think. Okay. This is again pressure drive. Okay, you see here, this now is GOR on, right? But what about the other plot? This pressure rate gonna be very big, and then it will decline fast. Right? You see here, this reservoir pressure also decline quite fast. GORs now going to the peak and then go decline back. Okay, this is how RTC the plot lah. Okay, to jive back with the performance of the reservoir. Okay. Now, second one, gas cap drive. Just now we talk about solution, right, in the reservoir. But here, you already have gas cap. Okay, this time around, GNG will calculate gas cap because it's a physical at the initial state, right? Yeah. So you can calculate gas cap. But still, in this case, you also have the solution gas. Okay. Okay, what happened actually? As you produce, the gas cap will start to expand, depending on your M size. How big the ratio between gas cap and oil. Okay, if you have very big M size, you might end up with a very lot of gas production. Similar to the solution gas. Okay, as you produce solution, oil, right? The gas will come out from the oil, and then it also can form a gas cap. That we call it the secondary gas cap. In this case, gas cap is the primary. It's already there. Okay. So, what happened actually? Okay, this very long explanation. But basically, more or less what I explained just now. Okay, let's focus on this one. There's a gas cap drive. Production decline is less significant than solution gas drive. Of course, because we have more energy as compared to solution, right? So you expect the decline production is gentler as compared to solution gas drive. Pressure declines slowly depending on gas cap size. I mentioned earlier, it's dependent on M size. Initially, GOR is steady but increased rapidly later as gas bypass oil. Okay, we'll see. We discussed for this one. Water production negligible. Okay, of course, in this case, it's assuming that only one drive. But of course, if you have like Baronia, right, sandwich, right, so you expect water. Okay, but in this case, it's assuming that only gas cap drive. Okay, the recovery, you see here, it's start to move a bit, the range, 20 to 40% of spike. Okay, it's better. So you need to put the well location away from GOC, not too close to water contact. There is a contact or water. Okay. Now you see here, let's focus on this one, GOR. Remember, the solution is now is go to the peak, right, and then decline back. But what happened to this GOR for the gas cap is increasing. Why is different as compared to again?
See that GOC moving down.
Yes, because you have abundance of the gas, right? It's not for solution, because in solution you have limited, right? It's depend on the size of your oil, right? But in this case, you have external gas, which is coming from the gas cabin. Okay. But the critical for well location, when you want to place a well, you want to be away from gas, right? Because gas is interflammability is mobile than oil, right? So you expect the petrol will be happen sooner or later. If you place the well close to the GOC. Okay. Yes.
The drive. Is it possible that in the early production we have gas drive, and then after sometimes the water drive coming in?
It's possible. It's possible. It depends on the size of the drive, water drive. If you have the parameters also, process like permeability in your aquifer, those will impact your water equation. If you have big aquifer, but if you have low permeability in your aquifer system, right? So you expect your water breakthrough will be delayed, will come much later. But you have very big permeability in your aquifer, right? So you expect as soon as produced, the water start to come in early. So to answer back to the jet engine part, maybe from the seismic you see there is a big aquifer. But from the production point of view, you don't see much water. It could be because of that reason. Okay, I continue with the water drive. Okay. Water drive. The next one is water drive in oil reservoir. Okay. You have normally you have two types of the water drive. Edge water or bottom water. I think this purely depends on your geological structure. Okay. But basically, it's still water drive. Okay. So for water drive in oil reservoir, it's basically just simply that the oil zone communicate with aquifer. Okay. So you can have energy purely influx of aquifer water. The water will push your oil inside your into the wellbore. Okay. Pressure decline relatively slow. You will see that the performance plot there. GOR keep relatively low and stable. Okay, it might increase at some time, but it's still stable. Okay. Water production increase steadily. That's the indication of the strong water drive. Operation decline when water breakthrough. Okay, means that you have quite stable production decline. Sometimes, but once water, you see the water breakthrough, the production start to decline. Substantially. The residual sweep depends on mobility ratio. Okay, it's just that mobility ratio is the viscosity of the water and the oil. Okay, it will be favorable recovery if you have large aquifer. Low oil viscosity, because what happened? It will improve your mobility ratio. High relative oil mobility. I think what we discussed earlier, the curve, right? Little reservoir rigidity and stabilization. Okay, so you expect that if you have, even you have strong water drive, for example like Baramba, right? If you have big, you have a lot of rigidity, and you still expect that the recovery will be low. Although you know that you might can achieve 40% recovery factor, right? But because of this rigidity and acidification, so you still have at the low side of the range.
Quick one.
Yes.
From RT point of view, water breakthrough tu you start when water cut or water besar.
Okay, it's not that how we mean water breakthrough. It's from your reactor. So we call it we come up with the bacterial rate, right? Okay, maybe it's advanced term, but from that, we can determine what will be the average saturation, average saturation at the breakthrough time. Okay, so you can know how much percent saturation. Okay, but to that doesn't mean that if you have saturation system now, right? So it will be breakthrough more urgent. It's depend on that's.
So there's an analysis that you can go through to conclude that water breakthrough started.
Okay, let's see. Okay, this is the reservoir performance. So reservoir pressure. You see the pressure decline is still decline. Of course, you have to decline the pressure, right? Otherwise, how do you get in your reservoir into the reservoir? But what's the main highlight here? The pressure is pretty much constant. It's stable. Okay. Gas flow ratio, yes, like Zam mentioned, right? You expect that it's more or less maintained at the RSI. Yeah. For the oil, you can see that it's much gentler. You have peak, right, and then it's gentle because of the reservoir pretty much maintained, right? And the water, this is the I would say that the glaring characteristic. You can see the water keep increasing. Sometimes in the graph of what you can see that towards the late late life wells, you can see that the water cutting, probably more than 95%. It's a lot. And you can have a long tail actually. And so at the time you have to decide when you want to abandon, depend on your economics. Okay. So with all those draft mechanisms, you call it the solution gas cap, and also what water drive. So you can have the combination. It's not just only one, right? So it will be a dominant drive mechanism, which depend on the strength of each sources. In this case, we identify that 1% drive indices from the material balance point of view. And at a particular time, doesn't mean that if we say that it's gas cap, it start with the gas cap, right? Drive mechanism dominant. You can be at the stage it become weak, right? And maybe water drive will be dominant. So it's another time frame. Okay, this is like a textbook picture. For example, Baronia, right? So you have big gas cap, thin on rim, and water drive. So in this case, how do we place the well to really optimize the recovery? How do you want to place well?
Possible can be horizontal.
Horizontal, right? Horizontal. Closer to the gas cap?
In the middle.
In the middle of the column.
More, if you want more, I think maybe gas cap because we have article, right?
Gas cap too, right? Clear gas cap too. Okay, but is it in the middle? Is it closer to water? How?
One third for gas cap.
1/3. 1/3.
That's gas.
Okay.
One
Say
third.
1/3.
One third of the oil.
Halfway. 1/3 of the oil means that 1/3 from the
From the oil content.
water content.
Gas oil.
Gas content means that 2/3 to the water.
To the water.
2/3 to the water.
See, 2/3 from the gas and 1/3 from the water.
Why?
Because gas is more mobile, so you want to be further away from the gas compared to water.
Normally that's the rule of thumb, but of course it depends on your modeling lah. Okay. But normally you want to keep away from gas because the mobility, gas is mobile than oil, right? Yeah. But into the water and oil, they are not so much different.
So if gas, you are independent, right? But if water come, the well will be gone.
It will be the same case actually.
Can we produce the gas first?
Because if you put the gas, right, you end up with a very high GOR. So you end up become like a gas producer.
Produce the gas first?
Okay, you want to produce gas first. Why you say so?
Passion.
Because it's at the top.
And then,
And then,
but your product, but what you're gonna sell gas?
yes.
Lagi mahal lah.
This depends on your case, right? I mean, even meant for the oil. So why you want to produce the gas? That's one thing. Second thing, I think that's the most important. That this is your energy, right? You don't want to drain your energy, otherwise you will stuck your oil there. Right? Yeah. So as much as possible, you want to control your gas so that you want to blow down. Otherwise, become the gas get blow down. Normally, we do that towards you know already no more recovery from oil, and then you will blow the gas.
Recently we had one RC I-35N. 12 down tip, semua dah high buat kan, 12 up tip dari high bore. So oil tu dah thin lah kan.
Yep.
So we do gas kat dalam.
Yes, that's towards the end lah. But we don't do that at early stage because you don't have energy lah.
But let's say you can have the water diesel, more diesel, gas diesel, right?
It's okay.
So then we can do water diesel, we push up everything.
Yes.
We
Up.
push up, we can take,
Okay.
check everything.
Only water injection together.
Only water diesel.
Okay. The problem there actually. Okay, but I'll go a bit detail lah. Okay. You don't want to get your oil inside your gas can. Okay, that's why in Baronia we do gas injection and water injection. Okay, you want to squeeze the oil, but you don't want to move the oil inside your gas can. Why?
Again, the question?
Okay, the question from I
Me.
okay. We do the gas
Water.
water injection only. We push the oil. Yeah. My question is that okay, we don't want to do that because you might be pushing your oil inside your
Gas.
gas
Okay.
gas territory. Now, the next question is why you want to do that?
GOR increase a lot.
Your replacement block, but your operation is there.
Yeah, because you can move your competition. If the oil moves up, then you effectively not draining that rim. Kan? You want to maintain the rim to as close to the well.
Yes, that's the from recovery point of view, right? To basically to maximize or optimize. Another side is that you also why you don't want also to move here. I mean, you can drink later, you put your well here, right? But still you don't want to do that.
Then the gas will be in the oil too. No?
Yes, you're right.
You need the oil, you need the oil.
Lose the oil, why?
Because they come into the gas and become gassy oil, right? Something like that.
Okay, but you can place the later you can drill well, right? Inside your gasket, right?
Later on, if you want to take that bath, actually you get more gas with oil, right? That means you losing the oil.
Why? Yes, you're right. Why?
Gas easy to move.
Okay, the reason why, because you introduce another element. They call it the residual gas. Residual oil because of the gas. Earlier, you don't have here. But as the oil move inside the gasket, you will introduce another factor. You introduce the SOGR. Residual oil to the gas. So that one you cannot be recovered forever lah. So that's why you become lesser. Earlier you have, let's say for example 70% mobile oil. Now because of SOGR, right? Then you introduce another 20% immobile oil. So you left with 50% mobile oil.
Well, if we have this kind of game, we then push the oil, but we can Normally, how much oil we put
Oil.
into and then we can
How much?
how much the oil can be pushed into the gas zone? Is it percentage lah, roughly lah, roughly.
Actually, okay.
Wait, before that, when you push the oil into the gasket, it will be a separated molecule from the existing oil ring.
Separated.
Separated.
But I'll go detail. But I go to that first. So actually, percentage-wise, it depends on the how much you produce from gasket. If say you produce originally lah, let's say lah, you say apa tu you have 100 PCF on the gasket, right? If you produce half, right, and then you expect that you only driving the oil from bottom, right? You have one machine, right? You expect maybe half lah goes inside your. It depends on how much you produce on gasket. But in this case, maybe it's a bit hard to determine because there is also another element, the solution, right? Solution is there. It's not purely gasket. Yeah. But as much possible, that's why we try not to have high go. If you see well producing a lot of gas, high go means that you could be producing from the gasket lah. Yeah. That's why it's very critical to see the performance plot. If the solution, you know that just now you know, right, the behavior of solution, right? Dapat gasket means that you're gonna produce like a lot of gas increasing by the time. So you try to avoid that thing. That's why if you have gasket and water drive, you do the both. Gas injection as well, water injection, like in Baronia. Okay, so
We had to, we can, when you do both gas, how do you know how to control it?
So good question. We have the method. Let you see. You see how we do that. Okay. Now I think this is the last one. That for the graph is gravity drainage. Okay, what is mean by gravity drainage? So gravity, we know, right? Gravity like an apple lah. Apa tu? Newton, right? Newton, right? So okay, what happened? It's benefit from this, the tilted of the reservoir. So as you produce, for the gas, is less the density, right? Right? It will go up. For the oil, it will go down. So if you have a right angle, a tilted angle, right, of a reservoir, so you can benefit that kind of the drainage, gravity drainage. So it means that you're expecting that you have clean oil because of the gravity segregation. The gas goes to the top, oil goes to down, right? So in your perforation zone, over here, you expect that you're gonna have the clean punya oil. So that's the benefit of the gravity drainage.
So this is for the reservoir with NAG lah, free gas.
You can have a solution gas drive, or gasket. Yeah. But this one mainly on the example mainly showing the solution. As you produce, gas will separate from the oil, right? So because of the gravity, less density, gas go to the top. And then you have a more oil, kan? Lower section, and you can produce from there more clean oil also. Okay.
The location tu mesti bila gas contact lah.
This one sourcing gas drive, so you don't have to contact the cases. So let's see the comparison for each drive mechanism. Okay, in terms of pressure and gas corrosion strength. Okay, this is the reservoir pressure and then cumulative oil produced. You can see that the least production coming from the solution extractor. Okay. And then followed by gasket drive, and then the good one is from the water drive. Okay. But again, this is like assuming that you have all is the optimal well placement. Right. But for the case of that solution gas drive, you have optimum well. For water drive, you don't have optimal placement. So you might end up with water drive lower than solution drive. So just bear in mind that this just assuming that everything is at optimum state.
Okay, gravity drive is this common lah.
Gravity drive, you can benefit from if you have tilted the reservoir.
Yeah, but if you plot
Normally,
this on this chart,
actually for gravity drainage could be higher than water drive.
higher.
Higher.
But it's not very common lah, gravity drive.
Because you guys have that as well.
Satu kan drive berat angle semua tu kan.
Yeah, I mean depend on the structure lah. It's given lah. You got that there. So it's given lah. Yeah. It's depend on the reservoir structure. The structure. Okay. For the GOR, you can see that this kind of trend lah. You can see that like a gas cap as compared to solution. It's going up, right? As you produce. Water drive, because of the high pressure, maintain high pressure, they have stable G. Okay. Now you can have a feel compared to between all the drive, right? Okay. So that's why it's very important for us when we doing the HRA, RF parameter, right? So you guys will ask us why this kind of RF. So it goes back to what we understand. If you see that it's a gas cap, so you know already, okay, this kind of RF range you get. But you see that, no, it's a pure, clean oil, no gas. So you can expect already how much RF. Right. And then you have aquifer, different RF.
So let's say you have in the explosion phase, you have prospect, so there's no well in that prospect. How do you estimate the RF?
That's why it goes back to the GNG. If you are saying that no, we will not have gas cap, so you seen already what will be the range of RF. 500%, that's not right. So she gets running.
So just based on that. Or do we see like analog fields on the?
Of course, we can do benchmarking that one, but at least in the idea that before you want to challenge further kan, right? So you can expect for the subject gas drive to have 40-50% RF. But if you say that, okay, based on this estimate, I know that there will be a big aquifer. So in that case, maybe 40% will be, more or less a good cover factor. But of course, we will do the benchmarking.
Looking at the plot, the contribution from water drive is much higher in terms of the recovery factor. Normally, how much, now I'm taking from the model point of view, let's say we have certain amount of recovery, how much we need to consider the aquifer? Because as a geophysicist, I need to submit, to provide the map to the modeler. How far I need to extend into the water lake, okay, so that they can model.
Okay. If you're talking about, let's assume it's brownfield. Brownfield. Okay. Brownfield, there will be there is a lot of aquifer model, fat popish, carpet tracy. Maybe that's new term for you, but that's the model we use.
Okay.
But definitely we have to match the aquifer strength to our production data, especially for pressure. Okay, so sometimes what normally as a practice we will accept whatever given by the GNG. Okay, thing is that we will calibrate again. Do we need more volume? Do we need less volume? So then we will see. We will compare with the one GNG finding. For example, we need more volume. But as geophysics, you see that this much only. This is where the communication will happen. Actually, sebenarnya we need more volume from your reservoir, from the aquifer. Okay, so is that because of the pump term? Maybe pump is much better because for the volume point of view, you say that this must only is covered. But maybe you say that, well, actually because of the limited seismic coverage, right? So that's all we see only this area only. Yeah.
But what if it is in the green bin? Because sometimes, okay, for us, most of the time we just stop at the point. Ataupun we have the contact and then few hundred meters from the contact we stop lah.
Yeah.
Tak ada orang nak spend masa bawa tu kan. But then from the reservoir engineer point of view, how far that if there is any right, say I have volume 1, so I need to have at least 3 times of the oil volume. Maybe then we can extend our interpretation to the whatever reasonable lah, so that it can be the input can be in consider in the static model and then can be used in the dynamic model.
Okay, for us, the practical part is actually we if you see there is aquifer, just model within your boundaries. Because why? Because for us, in order to get this mesh, normally we use the analytical aquifer ataupun numerical aquifer. When I say analytical aquifer, it's the model lah, fat coverage, we will attach the reservoir.
Okay.
So
that it is not necessary to be mapped lah.
To be mapped, no. It's just that because aquifer is unknown. Even you see the metal balance equation, I don't know, maybe we not show the whole equation. It's always unknown aquifer. Okay, we input the production data to derive what will be the aquifer size. It's always unknown.
Okay.
So we do not need to spend our energy to that.
Let's say we have an exploration well, and then we do DST. So DST info would be valuable in predicting
We will know the boundary basically.
boundary je lah.
Is it infernal acting ataupun ni different boundary lah. Is it you expect dalam the water influx or not? Yeah, that's all.
Because it could be stratigraphic, mangly, or whatever. Right?
Yep. Still, for the aquifer, accuracy will improve as you produce towards the end, after end of life. Aquifer. And the explosion stage is just purely based on range only, and analog. That's all we can do.
Just wondering because
Yes.
Pak An bring on the DST. So from DST, we know the boundary of the reservoir that we ada cover, right? Because we test in the on the yes. But during production, can we, because let's say towards the end of the production, we produce higher water. So can we know the extent of the water? Is there any method or practice to calculate what is the extent of the aquifer from that?
Okay. To be honest, it's will always remain unknown, except only for the strength. Because like I mentioned, you have a lot of aquifer model you can match. Is it PI or is it based on the configuration of the aquifer itself? There's a lot of parameters inside. So with different reservoir model, you also can match, right? Yeah. But means that how big aquifer? I mean, you're talking about the coverage, right?
Yeah.
Talking about coverage, it's remain unknown because there are so many factors inside. It's not just like an area only. No, it's a perm also is there. It's the angle also is there. Yeah, so many factors inside. Yeah. Unless you map, I don't know lah. You can map the sesame apa kan? But still, the question is permeability also is unknown. Right? Yeah. So that's also part of the equation.
Regarding to the aquifer in my previous company, they do the regional study, and they even try to hide the kind of correlation between, because we know that go deeper, normally the interval quality will be getting poorer. From seismic, you can see the scan may be extended quite far from our current contact. Then look at the well that penetrated that area, they try to predict the reduction in terms of the porosity and come up with the permeability. Next time we say that if the permeability below 9, preliminary, then consider the even water there, but maybe not inactive water lah. So they try to predict. So at the reservoir, at the hydrocarbon, we have the positivity of 20, and then maybe one where we drill there in the water, we see the positivity reading to like the 15, and then they try to predict until where they can expect the better positivity maybe go to the inactive aquifer 5% or 10% positivity. And then they see that okay, might be for that particular reason. If the sand can be extended based on the deposition of everything, might be that is the maximum aquifer can support for the reservoir. Some companies do the reasonable interpretation. Because we know that in some of the areas, even we see the field nearby with the produce, and then we got our green field. Even quite a far, 10 kilometers away from our field, but when we do our exploration where we see division, right, quite a few. So that's showing that kind of connection, even through the aquifer, that kind of connection. But they only can predict based on the reasonable study.
And still subject to something like we mentioned. So it's a big unknown like quite different. Okay. I guess similar things lah. I think this is for gas reservoir. Okay. For gas reservoir, okay. Now we're talking about oil just now, right? Oil, you want to have water drive, right? Because that will be the more or less highest RF, right? What about gas? Do you want to have water and gas? What do you think? If you have water, it's more energy, right? So, can we recover more from gas? Energy, energy reservoir. Okay. So you expect higher recovery if you have gas water drive, the gas reservoir. Because for gas drive, you expect you don't want to have water lah, basically, right? Okay. Yes. It's a era for the because gas in water they don't match lah. Okay. As water get into the completion, you will keep the well lah, basically. Okay. So
as far away to a crest lah.
Yes. So normally for the gas you want to put the crystal, and then you want to outrun the water. Yeah.
But there's still more mobile than water.
Betul. That's why you want to outrun. Means that you want to place your well dekat crest, far away from water. So as you produce, right? Of course you have to of course ada pala chemical part all those things, right? So you want to produce the gas, the sun, everything, right? No. So you have to have right withdrawal, but still you want to outrun the water, because for the gas, the best drive is the gas expansion itself.
So withdrawal meaning you want to control your production, not
Betul.
just blast.
Betul. Because otherwise you produce, you might break your screen apa semua lah, right? So right withdrawal, but still outrun the water. Okay. So that's why in the gas reservoir without water, you expect very high recovery, and of course it's limited the landing pressure. Another aspect lah, your facilities. For the gas case, it's pretty much driven by your facilities. Means that the lower the landing pressure, the lower the delta P, the more you can produce. If you have higher landing pressure, when I say landing pressure, it's at the facilities. Just imagine, your reservoir is 5,000 pressure, and your facilities is receiving facilities is 4,000. So you have only pressure difference how much? 1000. Means that you need to have delta P, otherwise how gas will flow, right? You have 5000, you cannot move at all, right? Yeah. So the lower your landing pressure, so you expect delta P will be much higher. Means that you can produce more. Yeah, that's the critical aspect for the gas. That's why even though you don't have water, but your RF still low. Because of what? Because of landing pressure. Okay.
Landing pressure means dekat platform
Platform.
processing.
Normally we do revealing all those things to reduce the compressor cleaning and limit to go down so that you can produce more.
Itu typically dekat the hub ni, dekat the satellite platform pun ada.
Depend. Normally dekat it's depend on the unit pressure punya ni lah.
How they
Punya
set
node dia lah. Node dia.
Depend on the system.
It depend on the system.
The system.
Yes. Yeah.
Menarik.
But normally because you develop this hub, right? So some gas is full stream.
Yeah.
So it depend lah. You have to study dia punya.
Menarik. Sebab when we had this dengan SAR kan, we talk about pipeline capacity, where to evacuate, how that pressure.
All those things, all those will impact your.
But saya tak faham sangat lah. Kalau faham lah.
Tim PDR kerja.
Itu kena join MPF. The entire system.
Okay, now you have to some at least you have some why. Yeah. Okay, this just to to give a summary lah. The summary of the average recovery factor for each drive lah. You see here, the highest will be the gravity drainage. Actually, gravity drainage is just like macam additional element only. For example, like you have gravity drainage for the drive, right? So that's why it's always the highest at the top. Yeah. You can see that you can go average 50%. Okay? Gas cap to go 30%, water 40%, solution 15%. Yeah, but this just your reference only. When especially an explosion stage, right? So when you have you develop your HRA, you know that the reservoir is this kind of reservoir, this kind of features. More or less you can expect already what would be your recovery factor. Okay. But of course, this depends on your benchmarking, based on region, based on area, those kind of things we do that to have a further refinement on the RF.
They need to pattern to both gas and
Okay. More or less, yeah. Carbonate also about the same. Because what matter for us is the flow, right? Darcy flow. Darcy flow especially is depending on your K, basically, right? Yeah, and the pressure. Yeah. So you can have similar K with the carbonate or plastic, right? Yeah. And also conductivity. Yeah. Let's say if you have carbonate is limited conductivity, and then different low RF. Okay, this is for the gas reservoir. You see here, if you want to drive, it will be lower than volumetric reservoir or gas expansion drive. But let's say within the group itself, for example, like water drive for a gas, do you expect stronger water drive will have lower or higher RF? Let's say you have two different reservoir, right? One with the moderate, one with the strong water drive for gas. Which one you expect to be higher RF?
Moderate.
The weak. The weak or strong?
The weak.
The weak. So actually, can both be the answer because at the end of the day it depends on your well configuration. Okay. So if you are still away from your water, right? So if you have strong water, it also can push your gas. Actually, in that case, you might have better recovery. But for sure, if you have purely volumetric reservoir, this is the case.
But then as you produce the gas, how can the gas expand? So you keep producing the gas, the volume will
Okay.
reduce.
Yeah. No. What that means that the is impact on the possibility because of high pressure, right? Yeah. As you produce, gas will expand. That's what we mean. Yeah. But of course, by the time the possibility will be vary by the time. We are talking about the term here, gas expansion is that it's purely on the compressibility impact. Yeah. That's what I mean. Okay. We are on the dot. So before I finish, we will continue secondary after this this primary, after next session. Okay, before I end the session, is there any question? Maybe yes, please.
So you mentioned we have to match the production data and
Searching.
but for let's say the reservoir and that is sometimes we don't know because of how it's
Okay.
how do you determine which way, like how the water comes is the right one? Because
Okay, of course.
ada yang boleh from the water, from atas and you still get it match with the
Match.
production data kan. So macam how do you determine which direction,
Which
which
direction.
flow of the water?
It's same goes to the static concept, right? You have to the kind of modeling, right? So same goes to our modeling also. We also have the probabilistic modeling. The one that we make will be only one solution, right? You might have different solutions, right? So that's we try to cover. Yeah, we will do the different probabilistic kind of modeling. You might come up with a different solution. In that case, meaning to say that you have to capture the density of that, even though you'll be able to match, you will still subject to the density that dimension the angle of the aquifer contact, right? So that's also part of density. So we have to address that. So as you drill, you still subject to the density, which you can avoid. But more importantly, that we have to capture what your acidity in this case. That's very clear. Okay. Any more question? Okay, good. Yes, please. GCPD. Okay. For GCPD, gas cap pull down. It's basically you have the gas cap, for example, right? You have gas cap and oil reservoir. So gas cap originally is the drive mechanism to this oil. Okay, so as you produce, you have achieved the ultimate RF, for example, 40% rate. That, based on the understanding, that will be the ultimate RF. Meaning to say that if you produce for this reservoir, the reservoir, you won't get the good reserve. Means that you can commercially produce already. Maybe you can go further, but that won't be economics viable already. So that time you decide to drill well, produce ataupun you do the macam addition add earth in the completion to produce for the gas cap insulin. So that you blow the gas cap that time. Normally towards the end of life of the reservoir. And I just maybe I probably that. Okay, for example, you have this reservoir, right? So this is your original original contact you, choice A, initial contact you. Okay. As you produce, here is your completion, right? For example lah, macam tu lah, horizontal lah. Okay, you produce from this interval. So as you produce, as you deplete, this will be shrink, right? So you limited to this only. And towards the end, you dah apa tu, very small, very thin already. So you left with the very big gasket. So at that time, you will maybe add perf here, and then you produce the gas only, and then we call it the gasket blow down.
That will be the last lah.
That's the last. Habis. And you have to convert lah. Maybe you need to, you know, as a to top up
Facility.
I mean gas demand lah. For example, you have shortage or gases, right? And you want to produce lah. Yeah, like I said lah, because reserve is not just recovery factor. It's you have to commercially produce, right? Even at 20%, it seems like still low, right? But because of, if you want to beyond, you have to drill macam, you know, a lot of wells, all those things. Not economics anymore. So 20% will be your this is
Only
limit.
there's a bridge economic.
Not technical limit, but it's commercial limit, because reserve is have to be in tandem with the commercial part. That's why they blow the gas.
Aku tak ada pakai combustion yang yes, that
Oh yeah, I thought. Oh, you mean this one? You can maybe, but you maybe water dah dekat kan? Maybe. So in this case, you want to again go back to the cluster, right? Okay. So after this, we follow up. We follow this topic with the secondary recovery after the lunch session. Okay. I think that's all for me. Thank you very much.